could you have life based on liquid ethane and methane rather than water? Did all of a sudden Enceladus just become, move to the top of the list of possible abodes for life? Informally, we're using a number that we think 1 in every 150 star systems has a planet with life.
Wow.
That means billions of planets out there.
You may know that for years, NASA has been searching for evidence of life on Mars. But these days, the search for life elsewhere in our solar system has expanded well beyond Mars to a half-dozen places in the outer solar system. Today, here to tell us what NASA is doing to look for life out there is Dr. Randii Wessen, a manager at the Jet Propulsion Laboratory. Great to have you back again today,
Nice
Randii.
to see you, yeah.
So you were here a few months ago telling us about Mars
Right.
and the search for life there. But as I say, I know NASA really, there are a half-dozen places even further out where you're looking for life. But why don't you give us a quick recap of what's going on in Mars, or what we know so far about the search for life there, where things stand. Then we'll go on to
Sure. When it comes for the search for life, the first thing we're looking for is the basic ingredients. Are there organic compounds, carbons and hydrogens, energy source, sunlight, heat, something, and liquid water. Liquid water paired is the key that we're looking for. So on Mars, we're driving along the surface with the 2 rovers, Spirit and Opportunity, and we're trying to decide if Mars ever was wet in its past, because it's not wet today on its surface.
They've been going for how long?
Wow, we're in January already, so it'll be just about 6 years.
6 years, wow.
It's supposed to be 90 Martian days, so they're really rolling. Way past the warranty.
It's like dog years or something.
Yeah, right.
It's even more.
Yeah, yeah.
Okay, but so now NASA's looking beyond Mars.
Right.
So what's next?
Well, if you look in the solar system, we find that there are a number of places where you could conceivably have abodes where you could have life. The key, we believe, is liquid water. So as you move out from Mars, the first place we got intrigued by was on a moon around Jupiter called Europa. When Voyager went by there in 80 and 81, because there were 2 Voyager spacecraft, we saw this thing that was like a cue ball, all flat, very bright, like an icy surface with fractures on it. And we're going, wow, why is it so smooth? And then later on with the Galileo spacecraft, now you're talking about the 1990s, we were getting indications there might be a weak magnetic field there. And you go, wow, how do you get an ice cube to have a magnetic field? And the best we can come up with is that there's a saltwater ocean underneath this ice cap. Yeah, so if you've got a saltwater ocean, you've got an energy source, something's keeping it wet. You've got organic compounds everywhere, and you got the energy keeping it wet. So you got water, energy, and organics.
So now, will the ocean go under the whole surface, or what did you, any idea the extent of where?
No, we believe there's like a 10, 20 kilometer shell, and the whole next layer is all liquid water ocean. So it's a subterranean, terranean. It's an underground ocean. And the idea, it could be a very good habitat for life.
Now there's actually a mission planned to go to the moon at present?
Right. There's a mission that just got approved. It's called, right now it's got a functional name before it gets a fun name. So this is called Europa Jupiter System Mission.
Sounds pretty
It's
basic.
functional, right? It's before you give it a fun name. The rovers were called Mars Exploration Rovers before they became Spirit and Opportunity. So
any idea what the fun name is going to be?
No, not yet. We're too early.
Okay.
We're looking at a 2012 start to start building this Europa mission with a launch in 2020. And then 5 years to get out to the Jupiter system. And then what you would do is you'd spend a couple of years in orbit around the Jupiter system looking at some of the other moons before you're pulled up in orbit around Europa, trying to see how thick the ice shell is, does it have liquid water, is there stuff venting through fractures in the ice field, that kind of stuff.
So this is mostly going to take observations then, or just take observations from above?
Right, we call it remote. So you'll be looking at different types of light from a distance away, trying to see what the composition of the stuff on the surface is.
Now there had been plans for, you were telling me about, was it like a cryobot and a hydrobot or something like that? What was that all about?
When we first started getting indications that there could be liquid water underneath this ice field, we said, well, gee, how would you explore it in situ, being in that environment? And we came up with this kind of wild idea. It's called a cryobot, hydrobot. Cryo meaning cold, so it would be a cold robot, and hydro, a wet robot. It would be this thing that you would just drop on the surface of Europa, and then it would melt the ice that it's sitting on, and then suck up the water and then squirt it out its nose, and do this hot water jet in front of it so it starts sinking through the ice field. And by steering this jet, you could steer through the ice as you sunk through the ice. The ice would freeze behind you, and you get lower and lower, and you do this for 10, 20 kilometers. And then
we
when
could
you
have used that for our driveway when I was growing up,
Yeah.
by the way, in the snow belt.
there you go. And then you would pop out into the liquid water ocean underneath, and now you become the hydrobot. You become the sub that goes around. But when we studied it, we had all these really exceedingly tough challenges.
It sounds really cool.
Oh, it was great. But how do you get the data through these kilometers of ice and then back to Earth? We said, well, could you do a wire? But then as you had this wire tether out as you sunk through the ice behind you would freeze, and then it would shear the wire and cut it. So they said, okay, well, how about if you took a transmitter and you just shot one out every 500 meters, and then try to leapfrog a signal out through the ice, and that got to be more and more complicated. And at one point we just go, look, it's too tough. Let's put this on the shelf for 10 years and we'll work on something simpler.
And there was even the question, I guess, right, of how deep the ice, or how thick the ice actually was, or what if it's
right,
thicker?
we don't know what happens if it's 50 kilometers thick, or is there a weak spot where it's only 1 or 2 kilometers thick, and that's where you'd love to land. So
what if it comes out the other side?
Well, there's a rocky center. But you'd like to kind of map how thick the ice shell is first to see, is it the same thickness? How thick is it? And are there any thin spots?
And is that one thing this mission that's planned will do?
We'd like to bring a radar that would penetrate through the ice field to try to measure how thick that ice field is and do a global map of the ice crust.
Okay. Well, I know there's some other missions, and even beyond Europa. What's next?
Well, one of the things that before we leave Jupiter, the European Space Agency is going to do something in collaboration with the Europa mission.
Oh, wow.
There's 4 major moons of Jupiter, even though there are 55 in total. But the 4 big ones that Galileo saw, the big one, Ganymede, also was giving off a weak magnetic field, and it's got a low density. So some people are going, hey, maybe there's a liquid water ocean under that too. So this mission is supposed to be, we do our Europa mission. The Europeans would launch another mission their own at the same time called Laplace, after the mathematician. We'd both study the Jupiter system, and we'd go around Europa and they'd go around Ganymede. So it'd be a tandem mission. But another mission, as we now work further out into the solar system, is around Saturn. Saturn has this really wild moon called Titan. Titan, it's bigger than our Earth's moon. It's got an atmosphere that's thicker than this that we're in right now. So where this is 1 atmosphere of pressure, Titan is 1.5 atmospheres of pressure. Oh. We're breathing 78% nitrogen, they're 98% nitrogen. And now we've seen...
Is it really flammable?
No, we need oxygen to be flammable. There's no
okay.
oxygen. But what we're finding is it's got lakes and oceans, or seas, depending on how big you want to make the definition of. It's got these liquid seas of liquid ethane and methane. So now we're going, we know we need organic compounds, which Titan has. We know we need an energy source. There's a lot of energy source going on there. Is it the liquid part or the water part? Could you have life based on liquid ethane and methane rather than water? And it's like, wow. So this is just a whole new laboratory for trying to explore how those form.
But if there was life and it came to Earth, then it would blow up.
Oh, no,
so
it would fry. No, you like explosions, huh?
Yeah. We'll be right back with Dr. Randii Wessen. And we are back with Dr. Randii Wessen from the Jet Propulsion Laboratory today, talking about the search for life in the outer solar system. Okay, so you're telling us about Titan.
Titan. So one of these other missions after the Europa mission that we'd like to do is a Titan-Saturn system mission. And what this one is supposed to do is, it's got 3 components. You send a spacecraft that gets up to Saturn, and since Saturn is 1 billion miles out, rather than the 5 years the Europa mission is going to take to Jupiter, we're going to take 9 years to get up to Saturn. We're going to orbit Titan, and then it's got 2 other elements. One, we drop off the spacecraft, and it actually goes all the way down and lands in the seas on Titan, and it's supposed to float in the oceans or seas of Titan in this methane-ethane ocean. And the other element is a thing that we drop in that it's a gondola with a balloon. So picture a big balloon, hot air balloon with a gondola with a science package, and it's supposed to just float in the Titan atmosphere below the haze level, being at that intermediate height, just looking at the surface.
And that would be pretty cool, because that's the first time NASA's done that, right?
Oh yeah, we've never done a balloon, right. And this place should have what we have in terms of water here, Titan has with ethane and methane there. So it should have ethane main and ethane and methane rivers and oceans and waves of this stuff. So to be able to just float over this and see that would be really, really wild.
Now, is this mission already in the works, or it was But didn't the Europa mission
Well, what happened is
get
Europa
higher
and
priority?
Titan were in competition one-on-one, and for this next opportunity, because these big missions are usually kind of like once a decade, once every 2 decades, because it may be like almost a decade to build it and then a decade to get the mission done.
Now, is that because of the launch date or just the funding and all of the
It's really the funding
practicalities,
level.
or- okay.
I mean, these are multi-billion-dollar missions. The two went head-to-head, and Europa won. So we're going to build Europa in the teens, get there, launch in 20, get there in 25 to maybe 2030. You'd figure that a Titan mission maybe start in the mid-20s, but it may be 2030s or maybe 2040s before you get out there with that one.
Well, it's interesting too, though, that now there's so many possible places.
Oh,
it's kind of
yeah.
exciting. There's actually competition now to
There's
decide where
competition,
to
sure.
send the missions. So.
And in the Saturn system, we got another competition. There's this itty-bitty moon called Enceladus. The Voyager data back in 80 and 81, when we went by Saturn, we noticed something really curious about Enceladus. It was orbiting right in the middle of the E ring. Saturn has a number of rings. The big ones are A, B, C, D. There's a little F. There's an E ring out there.
Are there hundreds of them these days, they think?
Well,
Or
we go up to G, and
G.
there's an H that they're probably going to announce soon because
So
it's
just the big
yeah,
ones, but
the big
like
ones.
little micro rings or something? or
Well, what a
just
ring
all-
is, it's a series of ice cubes in a train. So how, when does one ring system start, another one start? It gets to be kind of arbitrary because it's just a sea of particles. But we break them up into major zones.
I see.
Okay. And we noticed that Enceladus was in the E ring. Well, there's only two things. One of these two things has to happen because of that. Either Enceladus being in the E ring particles snow down onto this little baby moon, or conversely, this little baby moon is active and it's spewing out material and it's making the E ring.
And at first the theory was, oh, the stuff was just raining
Oh yeah,
down,
nobody
right?
believed. I mean, how do you get a little, 300-mile across ice cube to be active? You're a billion miles away from the sun. The light level's 1/25th the light levels. How can you get this thing to be warm? And then with the Cassini spacecraft, which is in orbit around Saturn now, we've been looking at Enceladus, and we caught plumes erupting off of the surface. So we now know Enceladus is making the E ring. For the life of us, we're trying to figure out how do you keep it? How do you keep it wet at that cold temperature? And then we tried to fly through the plumes, have the spacecraft just go right through it. We've seen ice particles, which is an example of something explosively coming off of the surface. But we also see water vapor, which is indicative that there's something wet underneath. So now we're pretty sure that it's got at least some pockets of liquid water underneath its shell.
Wow. So that's exciting. So you have an energy source and you have possibly liquid water.
And organics are everywhere. So you sit there and go like, wow, did all of a sudden Enceladus just become, moved to the top of the list of possible abodes for life? It's like, wow, but there's so much we don't know about Enceladus.
Now, are there any plans for a new mission then given everything else on the plate, any specific plans to do anything soon about?
Well, Enceladus, this is just a couple of years old in terms of knowing that it's active, maybe 3-4 years. You'd love to see, well, gee, the Titan mission, when it's coming in, is there a way to change its trajectory on its inbound leg so that you can go by Enceladus a couple times? You probably don't have the capability to get into the Saturn system, orbit Enceladus, pop out, go to Titan. It would probably just be a pass on the way in, because it takes energy to do that. So right now there's no specific plans of an Enceladus only mission, but it just got really exciting.
Yeah, well but there's more. So we've got all of these, those, if that's not enough, there's actually even more the possibility around.
Well, yeah, that's Jupiter and Saturn. Uranus seems to be pretty benign, but we were blown away in 1989 when Voyager 2 went by Neptune. We found a moon that had active geysers. And these are nitrogen geysers, so maybe we think that you got this ice surface with maybe some dust particles in it, and the weak amount of light hits it, warms it up, and then it explodes. The ice, builds up the pressure, just explodes through the ice. But you got Triton geysers, cryovolcanism.
And how do they go out into, a good distance above the surface, or are they out of the atmosphere?
Yeah, because there's not much of an atmosphere to stop it, so it just gets ejected and just sprays out. So, but now you've got an energy mechanism, you've got organics everywhere, and if you're building up pressure, does that mean you have to melt the nitrogen to be liquid to build up the pressure to blow to drive this cryovolcano? So it's like, wow, you got Earth, you got Io, moon of Jupiter with volcanism, you got Europa with liquid water oceans, Ganymede with oceans, you got Titan. In Triton, there's a lot of active places now.
Yeah, it's very interesting that it's gotten that big that soon, because we always thought, you know, you'd have to go across the universe to find life somewhere else or something, and all of a sudden all of this right here in our own backyard. Now what about, but Pluto is too far out, or I guess it's not even a planet these days?
It's not even a planet anymore. It's really just a Kuiper belt object. It was just discovered before Gerald Kuiper proposed a belt of objects out there. So we just thought it was a planet back then.
But there is a mission going out there, though.
There's a mission that we launched this a while ago. This is called New Horizons, which is going to get out to Jupiter and, out to Pluto the year, I want to say 2014, 2015, sometime that time frame. And then it's going to go out into the Kuiper belt, trying to see an object out there, because we think those are the early building blocks of the solar system.
Well, also I wanted to ask you, there's been all kinds of talk in the news lately about water on the moon.
Right.
Now, we've heard about the man on the moon and all this, but I don't think there's much sign of life up there. But I mean, is it possible there's any implication for life on the moon, or what does water on the moon mean for us?
First, to using our terms correctly, we can't call it water. We have to call it ice.
Ice. It is ice. Okay.
So it's not the wet stuff.
Okay.
It's just ice.
Not liquid. Okay.
And it's really just atoms of this stuff. So you'd have to take football fields of this stuff and process it to get like a quart of water out of this thing. So we don't think there are prospects for life because of that ice on the surface of the moon, that water ice on the moon. What we do believe, it really helps expedite humans going to the moon, because if you have ice on the moon, you make these liter jars full of water that you can drink, and then you can take that H2O and hydrogen and oxygen, separate it to hydrogen and oxygen, liquefy it to a liquid. Now you have a fuel and oxidizer for rockets.
I've got an idea I want to pitch to NASA.
Go for it.
Moon water. We'll bottle it, we'll make a fortune, and it's my idea. Can I get the trademark?
Wait a minute. It's $100,000 per pound to get off of the Earth.
We'll charge a lot. We'll charge a lot.
It must have a great label.
But it must have really good health benefits, You could.
That's irradiated.
We'll be right back with Dr. Randii Wessen right after this. And we are back with Dr. Randii Wessen from the Jet Propulsion Laboratory today, talking about the search for life out there. And now, as if all these places in the solar system aren't enough, of course, there's the rest of the universe. But NASA is actually, well, what else is out there that we're interested in? Well,
the big questions, and there used to be a program at NASA called Origins. It's kind of changed a bit, but the emphasis is still the same. You want to find out how life started on Earth, and you want to find out if we're alone. Well, that's too big a problem, are we alone? So you break it up into smaller problems. And what we've been doing is saying, okay, are there other planets out there? And NASA's getting pretty good at that. And it's not just NASA, it's actually ground-based observatories. Right now, I think the number is 422 planets outside of our solar system.
Because even in the news, you'll hear like, they discovered another planet or something.
But most of these things are hot Jupiters. They're really big, they don't have a surface, they're really hot. Their year is maybe 3 Earth days long, so they're just getting fried. But you want to find the smaller guys that are further away from the sun in this special region we call the Goldilocks zone. Not too hot, not too cold. And you want to get a rock in the Goldilocks zone to see if it has liquid water on its surface, because you got energy, you got organics, and now you got the liquid water. Those would be the places to look for.
Now, have we found anything in the Goldilocks zone?
We're not good enough yet. Right now, we're still finding what we call hot Jupiters. It was the end of 2008 where 3 different observatories actually produced the first images, and they're just points, but the first images of planets around other star systems. And the reason why that's such an accomplishment, if you think of how much light comes off the sun versus a planet, the reflected light, they say it's like trying to see the light being reflected off a nickel, when a nickel is about 1 inch away from one of those massive searchlights. And they're both 2 miles away. And usually it's a foggy day, so you got zodiacal dust. So that's the problem we're trying to figure out. How do you see that nickel?
But they were actually able to...
So those are the first images. So we believe we're probably a couple of years away.
It's not just dust on the lens or something?
No, it was moving.
Okay.
Because once you can actually see the light from the planet, you do this thing called spectroscopy, which is you look at the color of the light. Think about when you're in the freeway. White lights are mercury vapor, yellow is sodium vapor, whitish pink is high pressure sodium. So just by looking at the color, I can tell you temperature, pressure, composition. So if I can isolate the light from that planet, I can tell you what gases are there, and if I can see things that are out of equilibrium, things like ozone, chlorophyll, I couldn't tell you if it's a microbe or a cow, but I can tell you something is alive on that world.
So that's what you're calling the biomarkers?
Biomarkers, something that's chemically out of whack, that physics and chemistry say shouldn't be there. It means somebody's going, They're metabolizing it.
So it's interesting. So even halfway across the universe, we could actually have some sense of.
It's not halfway. I mean, it's 100,000 light years. You know, we're looking in the 20 to maybe 400 light year region around us.
Is that the extent then is how far out we could go, or
this
could we
is a tough problem. Yeah, right. So we're
I
just
want it all,
yeah.
you know.
We're finding planets typically within a few hundred light years of Earth, and if that radius of our galaxy is 100,000 light years, a couple hundred light years, we're still just in our neighborhood that we're just querying to see if we can find planets and then look for biomarkers on those planets, and we're not quite there yet.
And what about, but there actually were some missions that are planned? Or
we're
planned
designing them, and it's a function of how fast we can push the technology and when we can get funding for them. So the two that were really kind of interesting were called terrestrial planet finder. One's a coronagraph, where you take a disk and you put it over the star so you can see the planets next to it. And the other one is called an interferometer. We have a bunch of flying spacecraft, and what they do is they all look at the same star at the same time, and they play with the light in such a way that you get in the image the star to disappear, and all you're left with is the planets. So it's a nulling interferometer, and we're just working on that technology to do this. Because what you're trying to suppress is the light from the star versus the light from the planet. It's like 10 billion to 1. So for every 10 billion photons, you take 9 billion, 909 million, and throw them over there, and take the one from the planet. Take the next 10 billion, take the one.
So how far away do you think that technology is?
In a laboratory, we're getting really pretty close to doing those kind of nullings. But just because you have the technology to do it, you still have to design it, build it, construct it, test it, stow it, launch it, deploy it, calibrate it, use it. There's still a lot of pieces to this game. But if we had the funding, we could start the thing now. But right now there are other missions that are before it that really are more mature that we really want to get going first. So
the Europa mission is the first?
Europa is the next flagship mission, the multi-billion-dollar stuff. A Mars mission is like $400 million. A multi-billion-dollar mission, that's a flagship mission that you do once a decade or so.
Well, you used to hear about the Drake's equation,
right,
for figuring out the odds of life out there, right, or the how much life is out there, if life is out there. How does this change all of that? I mean, now that you've got so many places in our own backyard, let alone these other planets that are cropping up all over the place.
Well, Frank Drake, when he came up with that equation in the 60s, was trying to take the problem, is there life, and break it up into a number of small pieces. How many stars are out there, what fraction of stars have planets, what fraction of those planets have habitable environments, which could have life. So it was a good way of handling it, and we're actually learning some of these terms. My personal feeling is where I think we go awry with the Drake equation is he said, what's the difference between life and an intelligent life? Oh, intelligent life is anybody who can deal with radio waves. So using that approach, you're only looking for life forms that deal with radio waves. But humanity may only deal with radio waves for, we've done it for 100 years. Maybe we go 150 before we do laser communications. So in some ways, the Drake equation is really kind of myopic because it's only looking for intelligent life that's as intelligent as we are. But we are learning those other components of how frequently planets are.
So we could be missing a lot.
Yeah, so I don't think we should limit ourselves with just radio waves.
And what is your best guess for how do you, the possibility, if it used to be one in this and one in that, and if there's so many planets and so many habitable, can you kind of walk us through what you think the math would be on how to even calculate?
We're getting some data, but some of this stuff is just a logical extrapolation where we're going on kind of pretty flimsy ground making a statement. It looks like if you look at stars that are our size, F, G, and K type suns, our size the last 10 billion years or so, it looks like 1 in every 10 stars has planets like Jupiter's, hot Jupiters. Well, if it's 1 in 10, if there's 400 billion stars in our galaxy, that's 40 billion Jupiters.
Wow.
Now, we're trying to find the Earths, which are much smaller than Jupiter, which we can't do yet. Anecdotally, people think small planets are easier to make than big Jupiters. The universe just makes small things. If I take a plate, I get a couple of big pieces, some small pieces, lots of dust. I take an interstellar cloud, it makes a bunch of O stars, a bunch of F, G, and K stars, tons of little stars. So maybe little planets are easy to make. So informally, and this is where we're going out and just kind of making things up, informally we're using a number that we think 1 in every 150 star systems has a planet with life.
Wow.
That means billions of planets out there. Now, when we say life, this just could be soup, advanced sludge. This could be just microbial single-cell stuff. but we think that life may be relatively common. Advanced life, multicellular stuff, and definitely intelligence, that's the rare thing.
And any thoughts on how to even attempt to calculate something like that?
Oh, man. Well, you know, as you get further and further, it gets more and more speculative because you have less and less data to go upon.
Sure.
Since we haven't found any clues about other life out there yet, that would tell us that intelligent life should be very rare.
Very rare.
Yeah.
Well, we talked a bit on the phone, not to put you too much on the spot, but
sure.
You know, there are usually the idea that this could raise all kinds of philosophical, religious,
yes.
political,
yes.
all sorts of questions. But yet you made an interesting comment. You said, well, actually, sometimes it hasn't. People just kind of get used to it and go on. But anyway, what will this mean, that if we...
Well, you see, sometimes people put a lot of stock in something when it becomes kind of like a no-brainer. And my analogy would be, when I was in undergrad, the Holy Grail was finding planets. Well, in '94 we found the first planet. It made the cover of Time and Newsweek. Everybody said how this is going to, you know, change our outlook on the universe. It's going to, you know, it's going to change politics and religion. And no, of course there are planets out there. Most people don't realize there are 420 some odd planets out there. Well, you can figure maybe 10 years from now we're going to find the first planet that's got biomarkers on it. We don't have a prayer of going anywhere near that distance. I mean, my Voyager spacecraft that I started my career on, I was doing 1 million miles a day. At that speed, to get to the nearest star would be 80,000 years, and we're not even going to the nearest one. So, you know, we're going to find a planet with biomarkers. It's going to make the cover of Time and Newsweek. Everybody's going to say, oh, wow, it's going to change politics and religion. And then a year later, it's like, of course there's life out there. How can you think it was going to make a difference? But we're the advanced intelligent life, and we'll see how long we can hold on to that.
Well, hey, I saw Avatar. I know it's out
there. There you go. You just have to be blue.
Yeah, it'll match the set.
There you go.
Well, thank you very much, Dr. Randii Wessen from the Jet Propulsion Laboratory.
My pleasure.
Pleasure having you back. Thanks, everybody, for watching. We'll see you next time.